Good afternoon. I hope you can all hear me well. Perfect. I have the luck that I'm the last presenter of the day before we have the closing party. Hopefully everybody is still awake and anxious about this presentation. As mentioned, my name is Hans Klos. Sintecs. I think I'm already working with Siemens Mentor Graphics for more than 25 years in signal integrity. Started doing the work in 1995, XTK. Some people know XTK in the back. Then I was working with ICX, and I think the last 10, 15 years with HyperLynx, doing all kinds of simulations, signal integrity, power integrity, DDR timing, and doing that as a design service company within Sintecs. I'm going to talk a little bit about DDR. Um, Maybe a question. Who has experience with DDR4, DDR5 simulations, designs here in the room? See a few of them. Um, I think more than 10 years ago, I started doing signal integrity, multi-gigabit, and then we had signals running at 10 gigabit, and we had to do all kinds of simulations. So we had to pay attention to your stack-up material. We had to pay attention to the simulation models, all kinds of equalization we were able to do within HyperLynx. And now suddenly we have DDR4, and mainly if you're looking at DDR5, LPDDR5, we have a lot of new challenges. Those signals becoming faster and faster, and you cannot treat them as you did before by just following the guidelines of the manufacturer. Few things, maybe you did some simulation, but you need to do much more. That's what I'm going to tell you in this presentation about the challenges what we see. So on the right you see a little bit here from DDR1, 2, 3, 4, 5, and if you're looking at DDR6, it's going even faster. So what you see here, at least the clocks, and I just found out this is not correctly the LPDDR5 because the LPDDR5 it's a lower clock. Instead of 2 times, it's 4 times. So here we have a small issue for the people who noticed. But what we see at least here as well, if you're looking at the bit period from DDR2, was nice. We had so much margin, it was easier to develop. But if you're looking currently DDR5, LPDDR5, we have a lot less margin. So if you're looking at signal integrity, we need to pay attention to a lot of things like insertion loss. Insertion loss is playing a more bigger impact on DDR5, LPDDR5 than what we had in the past. Also return losses, crosstalk, and of course if you're looking at our timing margin from LPDDR4, DDR4, if you're looking at the timing margins, it's almost half of it. And that makes it very difficult. A lot of impacts on signal integrity. It will decrease your timing. Maybe your design is not going to work. So if you're looking what else, in DDR4 we had to pay good attention to our DDR, so DQS signals, DQ signals. But now in DDR5 we also need to pay more closer attention to your command and address signals because they are also running at double data rates. A nice thing what we also had already in DDR4, but in DDR5 is this decision feedback equalization. We also now have it for our command and address signals to improve the signal integrity. And all of this means that we need to do more simulations to make sure that our design is going to work. One hand with signal integrity, but on the other hand, we saw it already in the previous presentation, looking at your impedance profile, these kind of things. Well, in DDR5, LPDDR5, we also need to be aware of your impact of the power. So we need to look at your power, supply impedance, looking at noise margins. And if you're looking at the DDR4, LPDDR4, JEDEC did not supply any information for your supply impedance. But in the new JEDEC specifications for DDR5, LPDDR5, we get this information for the DDR5 and LPDDR5 interface. So what we need to do is that we need to do an AC decoupling simulation and a network analysis to optimize the whole design. besides the standard issues, signal to power integrity issues, if we are going to simulate a design, we also need to have IBIS models, IBIS AMI models, because the standard models for signal integrity, well, actually it's multi-gigabit type of signals, DDR5, running that fast, and that means that we need to have better quality models. But also, if you're looking at all the equalization, what is possible within a DDR5, we need to have AMI models. And other thing what we also need to do is we need to have a look at your VIA topology, because VIAs plays also a very important role, as we had it in the multi-gigabit interfaces. We see it now as well in DDR5, LPDDR5. And if you're looking at a DIMM, that's also one of the things. Now you have on your DDR5 DIMM, you have your network, your IC for power, your power management IC is already there. So instead of having the 1.2 volts feeding your DIMM, you now have it the 12 volt, and it goes to a PMIC on the DIMM. It's all because of your power requirements you have for DDR5, LPDDR5. So if you're looking at things that you also need to be aware of next to the simulation models, it's also need to look at insertion loss versus the length of the channel, glass weave effect. So standard FR4, can I still use standard FR4, or should I use now different kind of materials which have maybe better consistent dielectric constant? Maybe looking at the dielectric constant variations between different layers on your PCB. I need to look at my connectors, for example, or other kind of components on my board. Are they still capable of handling these signals? And also one of the things that's also important, thermal management. Because your power rails are getting lower, but if you're looking at the energy that it's put into it, with rise and fall times, which is probably 100 picosecond. I think when I started 10, 15 years ago, I had 100 picosecond rise fall times for the multi-gigabit signals, 10 gigabit. But if you're looking now, you have the same type of rise and fall times. So a lot of new challenges you have then. If we then look at our PCB layout, so we need to have a look at impedance specifications from the vendor guidelines. So if you're looking at the vendor guidelines, well, it's very sad to see that, well, it's very limited information in it. And if you're looking as well in the information, you see some things about skew time requirements. A skew, I think what was it, 1 picosecond within a byte lane. 1 picosecond. Well, 8 picosecond is approximately 1 millimeter. So 1/8 of a millimeter, you need to match the length in a byte lane. 1/8 of a millimeter. And if you're then looking as well to the software, like Expedition and your layout software, you're not typing in 1 picosecond, so you need to type in length. But length on an outer layer or an inner layer can also be different. So it's almost impossible to do it if you're following the guidelines of the vendor. The other challenge what we also see is the power requirements. And if you're looking at the stack up, I already mentioned PCB material. You need to have a look at different kind of materials which are capable of handling high-speed signals. In the past, it was not needed, but for these designs, DDR5, we need to. VIA topology. Well, actually now with rise and fall times of 100 picosecond, your VIA is also on transmission line. Means that VIA stubs, if you're looking at your rise and fall times, your VIA stub is very important. Layer configuration, where do I put my signals? And also looking at impedances to make it sure that the impedance of the whole chain is good controlled. So here you have something like different kind of PCB materials, but standard FR4 glass weave, it's almost impossible to use. Depending, of course, the length you have, but if you have a lot of devices, yeah. So what do you need to do when implementing a DDR5, LPDDR5? Is we need to do a pre-layout study, so topology study. So we need to explore maybe different kind of stackups we can select from vendors. Yeah, general parameters like this losses, stub length, crosstalk, impedance, the on-die termination. And if everything seems to work out, well, you can start with layout. But if you're looking then At the guidelines, so I already mentioned that vendor guidelines, they are difficult to read, but at least they are a good starting point. Um, Important one is flyby topology. Please use that. I still recently had a design, DDR4 design, and it had T-shaped topology, DDR2 style of routing. And then they had issues that could not match the maximum performance, had issues in power. And please use always for the DDR5 the flyby topology. You also need to pay attention to clearances in the breakout and in the via transition areas. Very important. Crosstalk, so via to via crosstalk. I'm seeing already impact of that. That you think, wait a minute, via to via crosstalk. Yeah, you need to pay attention to that. So make sure that you have enough clearances between two vias. Also, the clearances between the two traces. So this is your height between the trace and your plane. Make sure that you have 3H clearance between the signals. And if you're looking at clock signals, it needs to be 5H between a differential pair and the next signal. If it's not possible within your design, please simulate. You can simulate it. Routing symmetry. Make sure that symmetrical the routing what you do to prevent common mode noise. I already mentioned matched length. So 1 nanosecond or 1 picosecond, it's different in delay, in length, depending where it is routed. Ground planes, solid reference planes, and keep return vias close to the signal. I prefer to do it as close as possible within 2 millimeters. So if you're switching from one layer to another, make sure that you make a very good reference path, return path back for the signals. So close by, place these stitching vias for your return loops. And stubs, 100 picosecond rise and fall times, and if you take 20% of it, 20 picosecond, 8 picosecond. So you need to be aware that via stubs can also play an important role, especially if you have very thick boards with maybe 24 layers. How long is your stub? So I think here I have an example of an Intel HyperLynx DDR5, which you see length matching between the DQS and the clock, 25, but here you see at least within the DQ DQS, see it, what is it, 1.5. So it is already very tight limitations. And recently I had an NXP IMX, was it 95, and they specified 1 picosecond. It's impossible for a layout engineer to do. So we need to simulate. As mentioned, I'm using HyperLynx for doing this simulations for the high-speed memory. And I mentioned already that, what do I need? Simulation models for the DDR4 and DDR5 are different. For DDR5, I need to have these AMI models. So this equalization effect I need to take into account to be able to do it. So like the decision equalization algorithms or other type of algorithms, you have it in your simulation model, and for that you need the AMI. Nice thing of HyperLynx is you can have a whole DDR batch wizard, and they have also a DDR batch wizard, of course, for LPDDR5 and DDR5, where you need to provide some information. This one is always tricky. Time model, you'll get it from your memory vendor. So if you are using a memory device in JEDEC compliant, which there are, you get a timing model for the memory, but for the CPU, for the driver, you need to create your own model. Talk to about that a little bit later. Your device models, like now AMI models, you need to have your board file, ODB++ or the layout database, some other kinds of information for crosstalk power aware, and at the end you will get a nice result. Does it fail, pass? You can see your waveforms and also the eye diagrams. So all these information you can do is run these simulations within HyperLynx. But for the running a DDR batch wizard, I mentioned already that power is very important. So you also need to take into account the effects of power during the timing simulations for DDR. If you're looking at the difference between DDR4 and DDR5, it's also your eye mask. So for a DDR4 eye mask, we see it as a standard square eye mask. But if you're looking for DDR5, we have this, what do you call it, kite-shaped eye mask. So we have a lot of some more parameters to sweep. So equalization added to make sure that the signal has enough margins for this. For this simulation, we need the AMI models, but not always we can get these AMI models, especially if you're front runner in a new chipset. AMI models are not available, or it takes a lot of time. Well, maybe you can do something with some default models. So HyperLynx supports as well some default models for an DDR5 or LPDDR5. It's better to use them instead of, yeah, don't do anything. At least my experiences with these generic models, it already gives you a good overview what is possible. But for final, sign off, I would like to have the final IBIS AMI models. Do I get them? Well, unfortunately, it's becoming more difficult because a lot of vendors were not familiar to AMI effects, multi-gigabit type of simulations, and for them, AMI models are way more expensive to provide you than the standard IBIS models. So for them, it's also completely new to do something there and provide you these models. And often also the quality of these modules. That's a disadvantage with AMI. You cannot validate the models anymore as you did it in the past with the standard ASCII models. So if we are going to start to do a design, I mentioned already, first start with making your topology. So really looking, is my stack up what I selected? Is the drivers? Is my whole topology correct? So maybe first I'm starting often with very simple stack up with my driver model, transmission line via the main transmission, and going to the receiver and simulate it just DQ0, DQ1, for example, or a DQS signal. Just start with a few signals. And if that everything works, maybe you can also go to a complex one. Maybe I have a separate model for my package. Hopefully they supply it. Here, I have my PCB information. I have my DRAM package. And at the end, my AMI models for my top and bottom receiver. If everything is possible to achieve that, it's a good starting point to already start doing a more in-depth complex analysis. We are going to find out if we see some issue with components, connectors, figure out if the rise in signal bandwidth constraints. What are the constraints I'm going to set up? Well, rise time, I expect always something around 100 picoseconds for DDR5. But sometimes the models are not correct. And then you see suddenly it's never possible with this model to get this interface running at that bandwidth. PCB material, you can also play with it. Different kind of material. I'm using at the moment a lot of set planner for stack up, a lot of stack up material, because the standard stack up editor within HyperLynx, it does not give me all the information and all the needed information to run a simulation. So I'm using set planner as well for getting a correct stack up with the right material. Maximum stub length and trace length. Play with it. With how long can a trace be before it breaks down? If you're looking at a VIA, preferably you do not want to have stubs, but that's not always possible. So if you're through whole VIA, still you would like to use it. How long is my VIA stub, and is it playing a role into my signal? Because you're creating antennas if your speed of your signals are that fast. Crosstalk clearances. Crosstalk between VIAs clearances, how much they should be allowed. You can verify here already your timing requirements because you can run the whole DDR wizard already on this complex setup. What a lot of people don't do, and that's maybe, is these timing models for the controller. HyperLynx provides you a default controller model for DDR4 with some speed grades, but they are not sufficient. They are often a little bit too much margin. So what I'm always asking, at least, ask your vendor for timing models, timing information. So sometimes they provide you a complete timing model, like you see here. That's customers who have a lot of experience already of suppliers with delivering you a complete HyperLynx model. If not, ask them at least the AC switching parameters of your controller and make this model yourself. HyperLynx has a nice opportunity to do it within a wizard to set up your whole model. Once you do it a few times, you're used to it to create it for every CPU. And you can define it as well for different kinds of speed grades. So I always advise make your own model if possible. Yeah, if it's still not available, and unfortunately it's happening more and more, especially with some ARM chipsets, 64-bit, the latest IMX 9 series, they're not supplying you any timing parameters. We did some measurement, and we see that at least it matches a little bit. So it's better to use at least the generic ones instead of no models at all in timing, because you need to see at least what is the skew is allowed. So timing, important, but also if you're looking at the power. So if you're looking at traditional simulations, assume an ideal power distribution network. But if you're looking at DDR5, we need to take into account our power distribution, our complete power planes. So we need to do a distributed analysis because of the data rate up to 8.8 gigabit for DDR5. We need to take into account as well the switching of multiple lines at the same time. What does it have for an impact on your power plane? So looking at decoupling, what kind of decoupling capacitors, where do we need to locate them? So it's a complete analysis SIPI for these kind of high-speed interfaces. And sometimes you have a very dense board where we have some issues that maybe there is less space. Need to run spaces a little bit close to each other because we have no space. Simulation can help you then. So if you're looking at an ideal power distributed network, and if we're looking the difference between the one we set up in the analysis, we see at least that from an ideal PDN, we see that the margins are getting lower. From setup and hold, we see at least some less margins from top and bottom, eye width, eye height. So we need to take into account all these impact like simultaneous switching noise, via-to-via coupling, maybe through a power cavity we have on our board. We see a lot of more issues now with the signal trace return path issues. So make sure that your signal return path via is close to the signal. So if you're switching through a board, make sure that you have a via located as well to make sure that your return path is as close as possible to the loop. And that's what I'm seeing now, is that with DDR5, I still had customers that were capable in copying a reference board and still got the design working. When it fails to work, what was often the issue is they copied the routing, they copied the stack up, but they did not copy the same PCB material. They went to a different vendor with different kind of PCB material, and suddenly they had an issue. DDR4, the margins were already tight. But in DDR5, if you saw at least from 200 plus to 100 plus margin in the timing, it plays a very important role. You cannot copy only a reference board and think it is working. It is more than only the routing you're copying, it's also the complete power distribution network. So does it really make a difference at DDR speed? Yes, we need to simulate. So we need to simulate the impact of your PDN on your power planes. And we use HyperLynx, PDN and channel model extractor to guide you through this process. Nice thing of the previous presentation as well, how they explain at least reducing some decoupling capacitors. We can do much more with the HyperLynx PI analysis to make sure that your whole interface works with the correct noise levels when all the signals switch at the same time. This was also my last slide of my presentation.